One last thing we're going to be looking at calculating in this chapter is the energy change, or the enthalpy change actually, of a reaction. So here I've equated enthalpy and energy. That's not completely correct. The enthalpy of a system is more equivalent to the heat flow of the system. So energy includes heat flow and pressure volume work, but we're going to be concerned with the thermal energy, or the heat flow of a system, and that is the enthalpy. We've used the terms endothermic and exothermic before in chapter 3. Endothermic refers to a process where energy is being absorbed. So sometimes you have to put energy into a reaction. Not just the reactants and the starting materials are needed, but some energy is needed in order to make the products as well. So the products are higher in energy than the reactants, and we have to put energy into the system, thermal energy, and so the change in enthalpy is positive. It's kind of like an uphill reaction. Other reactions release energy, release thermal energy when they are conducted, and so those processes are exothermic. The products are more stable, they're lower in energy than the reactants. For example, when you're burning fuel, the fuel has a lot of energy stored in it, and in the process of burning that fuel, energy is released and the products are lower in energy. So something we need to remember is that an endothermic process will have a change of enthalpy in the positive direction. The delta H will be shown as a positive number, whereas the heat flow, or the enthalpy change for an exothermic process, is negative. In addition to being positive or negative, you might be given an actual numerical value for this delta H, this change in enthalpy. And if you are given a value, then that is for the reaction as shown on a molar scale. So what does that mean, that this energy is given on a molar scale? The way that the reaction is written in moles, 1 mole of nitrogen and 1 mole of oxygen producing 2 moles of NO gas, would be associated with a change in enthalpy of plus 182.6 kilojoules. So that change of 182.6 kilojoules is not for 1 molecule of nitrogen reacting with 1 molecule of oxygen, it's for 1 mole of nitrogen reacting with 1 mole of oxygen. So is the reaction endothermic or exothermic? We were just talking before about how a positive change in enthalpy means that you had to put energy into the reaction. The products are higher in energy than the reactants, so this would be an endothermic process. So this amount of thermal energy is absorbed in this process. Next, we are asked for the energy change that is associated with 3.77 moles of NO gas. So 2 moles of NO gas, commonly called nitric oxide, is associated with an energy change of 182.6 kilojoules. So this is the relationship. For every 2 moles of NO that are produced, 182.6 kilojoules of energy are required to be put into that. So what about for 3.77 moles of nitric oxide? If every 2 moles requires positive 182.6 kilojoules, then that 3.77 moles produced would require a change of positive 344 kilojoules for that process. All right, unfortunately we have a page break here, but here we have a negative delta H, and that means that the reactants are higher in energy than the products. Energy is coming out of this reaction. This would be an exothermic reaction. The relationship between the energy change and the hydrogen gas is that 2 moles of hydrogen reacting is associated with a negative 483.5 kilojoule delta H. So using that relationship as a conversion factor, we'll go ahead and work with 8.74 grams of hydrogen gas. All right, I'm just realizing that this is grams when our relationship has moles. So we are also going to need a molar mass, which for hydrogen is 2.016 grams per mole. So this molar mass can convert hydrogen from grams to moles. And then our next conversion factor we get from this relationship, which I moved out of the way over here, that 2 moles of hydrogen is associated with negative 483.5 kilojoules delta H. And so when we do this calculation, the grams of hydrogen cancel and the moles of hydrogen cancel, and we're left with kilojoules. My calculator actually gives me a lot of digits for this one, that it's negative 1048.062996 kilojoules. But since we only started with 3 significant digits in our mass of hydrogen gas, I went ahead and rounded it to 3 significant digits in the answer. Okay, here we have another thermochemical equation. Thermochemical meaning it's not just the chemicals in the reaction, we're also shown the change in thermal energy, the heat flow of the reaction as well. And so since this change is positive, remember that means we are putting energy into this reaction. It's like an uphill reaction. The products have more energy than the reactants. That is an endothermic process. Let's go ahead and write some relationships. That positive 65.3 kilojoule change in energy is associated with 1 mole of calcium hydroxide reacting because of the coefficient of this equation. It's on a 1 mole scale. Also, 1 mole of calcium hydroxide has a molar mass of 74.10 grams. We're going to need that relationship as well. Okay, starting with the moles of calcium hydroxide, if we have 0.875 moles of calcium hydroxide, we can relate that to the energy using this first relationship. We'll put the 1 mole of calcium hydroxide on the bottom so that it can cancel. 65.3 kilojoules of thermal energy on top. And so that is associated with the change of 57.1 kilojoules. If we start with grams of calcium hydroxide, we are going to need to convert the grams to moles before we can convert the moles to energy. And that conversion factor is just the molar mass. That will convert the calcium hydroxide to moles, and then we can use the molar enthalpy change from our reaction. So the reaction of 25.60 grams of calcium hydroxide would require the input of 22.6 kilojoules of energy. Okay, so let's take a look at these last couple of problems. Here we want to relate the heat or the thermal energy to the grams of acetylene. So we are going to need the molar mass of acetylene and also the information that this reaction of 1 mole of acetylene produces 1301.1 kilojoules of heat. So starting with the 62.5 grams of acetylene, C2H2, we'll go ahead and cancel that and convert it to moles. And then we'll cancel the moles using this relationship to convert it to kilojoules of energy. And so that comes out to negative 3,120 kilojoules of energy. So that's how much heat is released by burning 62.5 grams of acetylene. All right, let's write some relationships that we're going to use for this reaction. So this energy change of negative 355.0 kilojoules is associated with 6 moles of cobalt-2 oxide, and it's also associated with the production of 2 moles of CO3O4. So this is the relationship between the energy and the product, and also the relationship between the energy and the reactant that's being asked about here. I didn't write the relationship with oxygen because none of the questions have that. Since this amount is negative, that's the amount of energy that is coming out during this process. It's an exothermic process. If we start with 2.85 moles of cobalt-2 oxide, and we know that every 6 moles of cobalt-2 oxide produce 355.0 kilojoules of energy, then that would produce 169 kilojoules of energy. The next part, we're starting with a mass of CO3O4. So for this, it's helpful to have the molar mass. It's 240.79 grams per mole. So we'll use this molar mass as the first conversion factor, putting grams on the bottom so that they cancel. And then the relationship here, every 2 moles of CO3O4 produced will release 355.0 kilojoules of energy, and that gives a result of negative 39.6 kilojoules of energy. So 39.6 kilojoules of energy being released when 53.70 grams of product is produced.